Okay, it's 57. Hey, dudes, this problem is pretty time consuming. This would not be a multiple choice type question. This is more of a free response where I'm grading your work. All right, so we're looking for this electric field. The intensity of this electric field, we're told that it's uniform, which means the electric field here is the same as the electric field here, which is the same as the electric field there. You know, it's not changing. All right, we're given the mass of these charges. So these two spheres are equal and opposite. They have the same mass, 0.002 kilograms. You want to put grams into kilograms. What else do we have? The charge. Each of these guys is 5 times 10 to the negative 8 coulombs. Now the length of the string is 0.1 meter. Put centimeter into meter. 10 centimeter is 0.1 meter. And then this theta here is 10 degrees on both sides. Theta is 10. All right, the problem starts out with free body diagram. Each sphere has 4 forces. So what we're going to do is we're going to pick one of the spheres and do a free body diagram. It doesn't matter which sphere you pick, you'll get the same answer. So let's pick this positive guy right here. So looking at the positive charge, the forces are, so we have mg straight down. We have tension up at an angle like this. If this angle off the vertical is 10, then the angle from the horizontal would be 80. Okay. Now there's 2 more forces. Is this electric field exerting a force on the charge? Yeah, man, that's what electric fields do. Electric fields exert force on charges. So we have the force of the electric field. And by the way, what's the equation for force of electric field? QE. Okay? There's one more force. What do positive charges and negative charges do? They attract each other. So there's a force to the left, which is like a Coulomb's law force, right? So what's the equation for force between charges? K QQ over R squared. But these charges are the same, right? So we could just write KQ squared over R squared. Does that look familiar? So where did that come from? Force between charges is KQQ over R squared. The Q's are the same, so we'll just put Q squared. Okay? That make sense? Charges attract each other. Now, one thing we're going to need, guys, is this distance in between the charges, right? That's our R. We need to find the distance between the charges. Do we have enough info to do that? Yeah, just it turns into a trig problem, right? So focus on one of the triangles. You can solve for half of this distance, you know, by focusing on one of the triangles. So, you know, the way you would find that distance there is that would be sine of 10 degrees times 0.1, and then take that and double it. So it turns out that R, the distance of separation between the two charges, is 0.034729 meters. So that's our R there. Okay, so now what we're going to do is we're going to sum the forces. So we got our free body diagram, so I'm going to shrink this down, make some room. Okay, so we sum the forces X, we sum the forces Y. All right, in the X direction we have 3 forces. Oh, this is tension. So we have QE, right? That's perfectly X. We have KQ squared over R squared in the negative X. That's this guy right there. And then we have the X component of tension, which is cosine 80 T. Now, what will the sum of the forces be equal to here? Sum of the forces equals ma, but is this sphere accelerating? Nope, so it's equal to 0. All right, so we just wrote a very useful equation. All right, in the y direction, we have 2 forces. We have the y component of tension, which is sine 80 times t, and then we have mg down. Again, there's no acceleration in the y, so that equals 0. Okay, from here on, it's just algebra. Once you have this done, it's algebra. So take this y equation, solve it for t. The only thing missing in there is t. You get 0.0199 newtons. That's what tension comes out to be. Take that tension, plug it in up here, and then now you can solve this equation for E. The only thing missing in this x equation is E, and it comes out to be 442,000 Newton per Coulomb. Okay.